maybe since online, are there questions online? Okay. Okay, so today we are going to start discussing D-branes in superstring theories. So x mu, this is the usual space coordinate. This, of course, has n or d boundary condition. Okay, so n stands for Neumann, and that is for Dirichlet. And also in this, there will also be ns and r. So one shouldn't confuse between n and ns. Okay, so ns will be ns sector. So Neumann boundary condition on x mu corresponds to del sigma x mu equal to 0 at sigma equal to 0 and pi. And this translates to okay, because tau appears with the same sign in z and z bar, sigma appears with opposite sign. Okay, so del x mu minus del bar x mu will involve del sigma x. Okay, and that you are setting equal to 0. Dirichlet, on the other hand, corresponds to del tau x mu equal to 0. Let sigma equal to 0 pi. Okay. And this translates to del x mu equal to minus del bar x mu. Okay, and we have studied this in the bosonic string theory. This remains unchanged. And we also saw that this basically ensures energy conservation. World sheet energy conservation. In particular, the fact that the sigma component of the energy momentum tensor is 0. Okay, because that's what one needs for conservation of the energy.
There was some argument about why any other boundary condition is not allowed. Right?
Yeah, for one, yeah, I mean, what other boundary condition can you put? You can, of course, put linear combinations. That is allowed. I mean, there are some conditions, okay, where some linear combination of del x1 and del x2, for example, is set equal to 0. Okay, those kinds of boundary conditions are allowed, right? And you can see that it has to be allowed because you can imagine a D-brane which is at 45-degree angle in the xy plane, right? So that certainly is possible.
This to del sigma x mu equal to 0 and del tau x mu equal to 0 comes from this d sigma tau equal to 0.
Exactly, yeah.
What's it energy?
Yeah. So another question is, what about
General strength is also this boundary condition. Those come from this condition only, that what's it energy?
exactly, yeah. So the conformal invariant boundary condition basically come from that. So the general way one sets up the boundary condition problem is that you ask what kind of boundary condition will preserve the world sheet energy. Right? Then on top of that, you can impose other conditions if you want, right? Like some current you want to preserve, right? But those are not necessary. Right? Those don't destroy. I mean, even if you violate those currents, you don't destroy conformal invariance, right? But you give up some other conservation law. Here, for example, for the Dirichlet boundary condition, okay, you already give up the momentum conservation. Right? P mu is not conserved anymore. Okay, for Neumann boundary condition, momentum is conserved.
So it's like in some CFT, if there are some other currents and our boundary condition doesn't respect it, it's like
Yeah, suppose the CFT has some other symmetries, right? The boundary condition may break it, right? It doesn't destroy conformal invariance, so it's still a CFT, but it has less symmetry. Yeah. Okay. So what about the boundary condition on psi mu and psi tilde mu? And here, the first of all, psi satisfies a first order differential equation. Okay? So you cannot have a boundary condition that involves derivatives. Okay, so it has to be without derivatives. Okay? So the boundary condition in this case will relate psi mu to psi tilde mu. Okay.
So, given the fact that we have worldsheet supersymmetry, won't
Yes,
it automatically get fixed by what we demand on X?
but the boundary condition may break worldsheet supersymmetry, right?
Oh, that's the choice you want to make.
Yeah, meaning the point is you will see that it will be broken in some sector. You want to preserve as much as you can, but it will eventually be broken because in the NS sector, the global part of the supersymmetry is broken.
Okay.
Right? We have seen the G0, for example, exists only in the R sector. Right? G0 and G0 tilde, which are the constant supersymmetry transformation parameters.
Yeah.
So the global worldsheet supersymmetry will be broken anyway once you go to NS sector.
Okay.
Even in closed string sector, right?
I see. Okay.
But nevertheless, we don't want to break it badly because we have used the gauge symmetry, right? At least the local symmetry we have to use, right? So there are some, you have to follow some specific rules of how you can break the worldsheet supersymmetry. Okay, so the boundary condition leads psi to psi tilde, right? Because basically, again, just by the energy conservation, right, we want T and T bar to be related. Okay, so basically T and T bar should be equal. Okay, they actually relate psi and psi tilde. Okay. So you have two choices that preserve worldsheet energy. Okay, which means T sigma tau equal to 0. And that is either psi mu equal to psi tilde mu, or equal to minus psi tilde mu. Okay. This is assuming that the boundary conditions don't relate different sides. Okay, that it doesn't relate, for example, psi 1 to psi 2 and vice versa. Okay. So because the energy momentum tensor contains psi, right? It's quadratic in psi, right? So whether psi mu is set equal to psi tilde mu or psi mu is set equal to minus psi tilde mu, the energy, worldsheet energy is conserved. So T and T tilde are unchanged under psi mu to minus psi mu. Okay. So this means that either boundary condition conserves T. But now we are going to distinguish between psi and psi tilde. Okay. And so basically the way we do it, we demand that the TF sigma equal to 0. Okay. So TF is the supercurrent. Right? TF has a one worldsheet spinor index and one worldsheet vector index. So TF sigma basically refers to that worldsheet vector index. Okay. And it shouldn't flow out in the sigma direction, right? It shouldn't flow out in the boundary. Suppose you want to impose this condition. Okay. Then what you want is that the psi del x, this implies that psi dot del x would be equal to psi tilde dot del bar x. And this means that psi has, okay. So if see that for Neumann, del x and del bar x are the same. Okay. So psi equal to psi tilde for Neumann and psi equal to minus psi tilde for Dirichlet. Is that sigma equal to 0 pi. It's clear if you want the TF, the space component, okay, of TF to vanish. Okay, so if you think of the worldsheet as a strip, we are demanding that here there is no flow of TF out. Okay, then we impose these conditions.
That's at the boundary.
That's at the boundary. Yeah, exactly. At sigma equal to 0 and pi. But this condition can be maintained only in the Raman sector. Because in the Raman sector, so okay, I have not defined what Raman sector is, right? But let's try to get some insight from the closed string spectrum. Okay. For the closed string, Raman sector corresponds to periodic boundary condition along the sigma direction. Okay, so this means that psi del x, the zero mode of psi del x, because okay, this means first of all that del x is of course always integer moded. Okay, this will mean psi is also integer moded. Okay, so psi del x, this will also be integer moded. So its zero mode is a well-defined object, right? Because it has an integer moding, and that zero mode is the generator of the global supersymmetry, global worldsheet supersymmetry. Right? Again, you should distinguish it from the space-time supersymmetry. Okay, this is a global generator of the global worldsheet supersymmetry. So only in the Raman sector you can maintain this. Okay, maintain global worldsheet supersymmetry. In the NS sector, right, whatever way we want to define it, it is clear that you cannot maintain global worldsheet supersymmetry. Right? If there is no analog of G0, then there is still local supersymmetry, but not global supersymmetry. So you expect that in whatever way you define our NS sector, in the NS sector we should have broken global worldsheet supersymmetry, right? Global worldsheet supersymmetry cannot be preserved in NS.
Are you saying simply because there are half integer modes in the NS while
exactly, that's right. In the closed string, in the NS sector, there are half integer modes, right?
Yeah.
Okay, so that basically is showing that it is that you cannot preserve supersymmetry, right? G0 doesn't exist. Because another way of saying is the bosons, the scalars are integer moded, fermions are half integer moded, right?
Yes.
Clearly have broken the symmetry. Right? So locally you don't break it, because locally what happens is that you take supersymmetry generators which are half integer moded, and that's what relates x of integer moding to psi of half integer moding.
Yeah.
But the zero mode is gone, right? Supersymmetry is zero mode.
But that was fine in closed strings, right? We only had G half, not G0.
Exactly. Yeah, yeah. So it was fine in closed string. In closed string, it will also be fine in open string. Right? It's just that the global symmetry, supersymmetry is broken, right? Which is what we are demanding, right? We are demanding that TF sigma is 0, right? Why are you demanding TF sigma is equal to 0? Because integral of over d sigma Tf, we want to be conserved, right?
Yeah.
But integral of over sigma d sigma of Tf, right, gives the zero mode.
Yeah.
And that doesn't exist in the NS sector.
I see.
Right?
This is not an open string problem, though. But
No, this is not an open string problem, right? I'm just trying to say what would correspond to the NS boundary condition in the open string case. Okay. So periodic, this kind of boundary condition is natural because that's what preserves Tf. Okay. But we know that in the closed string, just from the closed string analysis, that you cannot have Tf conserved in all sectors. Okay. So if you want to go beyond what you have done so far, you have to allow Tf to not be conserved.
In closed string also this in NS sector global supersymmetry was broken.
Exactly. In closed string also in the NS sector, global supersymmetry is broken. Okay, which is it's reflected in the fact that there's no zero mode, right? Global supersymmetry will be just integral d sigma Tf, right? And that doesn't exist there, right? Because that would generate the zero mode.
when you say doesn't exist, don't you mean Tf sigma integral is automatically Tf integral is automatically 0?
Yeah, you can say Tf integral is, well, I don't know whether it's, I mean, it's, the modes are such that it, yeah, I mean, maybe it will be automatically 0 because if you have something like e to the I pi sigma, e to the 2n plus 1 I pi I sigma, right? And if you do the integral from 0 to 2 pi,
Pi 0 to pi.
0 to pi, yeah. Okay, maybe n plus half. Okay. So this will be 0. Yeah, I think this will be 0. Well, it will be 0. Let's just check. This will give you e to the n plus half I times 2 pi minus 1, right? Over something, doesn't matter. So this, no, it doesn't give you 0 actually. It gives you some n-dependent object, right?
Looks like a minus 2 by something.
Because e to the, pardon? Exactly, yeah. It becomes ill-defined. So, yeah, that is a branch cut, right? So it becomes ill-defined, this object. Yeah, so this is, yeah, it's certainly not 0. E to the 2 pi I n is 1, right? But this is minus 1 to the n minus 1, right? Something like this. So you don't try to define objects like this, right?
That
We
is
define,
just minus 2, no? Well, what is the issue?
yeah, it is minus 2. So it's not 0, but it's something, right? But this is not well defined. See, the point is you integrate something from 0 to 2 pi, right? But assuming that there is a periodicity in sigma, right?
Yeah.
This is not periodic in sigma. So if you, instead of 0 to 2 pi, suppose you integrate from a to 2 pi plus a, it will give a defined answer,
Okay.
right? Is that clear? If you a to 2 pi plus a, right? What it will do? It is basically effectively shifting sigma by a. That will be defined. That will give a defined answer altogether to this.
Rather be a series, a sum over this actually, and because all modes will contribute.
True. Yeah, true. But look at a given n, right? If you try to do this integral, right, 0 to 2 pi, of course, will give some fixed answer. But suppose you want to do from a to 2 pi plus a, that will give a defined answer. Right? So it's in that sense that it's ill-defined. If it was instead to the 2 pi I n sigma, then a to 2 pi plus a will basically give you delta n0. Okay, there is an ambiguity in this answer over here. You have with 2 pi times delta n0. Is this clear? Right? Because you will get 1 over in times e to the 2 pi in, 2 pi, e to the 2 pi in minus 1, right? And that will be non-zero that will be 0 when n is not equal to 0. And when n is equal to 0, you do this separately. Right? Set n equal to 0, you get integral a to 2 pi by a of 1. That will give you the answer 2 pi. Is this clear? Okay, so let's turn back to the open string sector. Okay. So this is one observation that we cannot hope to preserve the worldsheet supersymmetry in all sectors. In the Raman sector, okay, this by definition is what we will call Raman sector. Okay, we can preserve it. The next observation that you have to make is that if you recall our configuration space, okay, that was the starting point. Our configuration space is when you take x, psi tilde and identify psi with minus psi, right, and psi tilde with minus psi tilde, okay, independently. So x, psi tilde is supposed to be the same point as x minus psi tilde or xi minus psi tilde. Okay. So if we are putting the boundary condition that psi equal to psi tilde, okay, you also have to put the boundary condition that psi is equal to minus psi tilde, because minus psi tilde is supposed to be the same point in the configuration space as psi tilde. Okay. So you cannot avoid having to put a minus sign here, because psi tilde and minus psi tilde are the same points. Okay. Now you can do various combinations, but the only inequivalent boundary condition that you can have is the following: that psi equal to psi tilde at sigma equal to 0 and psi equal to minus psi tilde at sigma equal to pi. Okay, you could change, you could switch. At the end, the final result will not change. Right? You could have put psi equal to minus psi tilde at sigma equal to 0 and psi equal to psi tilde at sigma equal to pi. So once you have chosen this for n, we put psi equal to minus psi tilde at sigma equal to 0 and psi equal to psi tilde at sigma equal to pi for the. This, as long as both ends have n boundary condition or both ends have d boundary condition, n and d really doesn't make any difference, right? We'll right on the mode expansion, we'll see that n and d doesn't make any difference. Okay. But sometimes you may have an open string whose one boundary is on a has Neumann boundary condition, the other one has Dirichlet boundary condition. Okay.
Just that, like we saw here, generally that means psi equals psi tilde or psi equals minus psi tilde for my condition.
Yeah, but here we are saying that even if the boundary condition is Neumann, that is fixed by x, right? Even if the boundary condition is Neumann, you have to allow also a different boundary condition on psi, okay, where you change the equality of psi and psi tilde to with a minus sign at one end. Okay. This, by definition, will be what we'll call NS sector. This is the NS sector states. This is our sector. These will be our definitions. Okay, the invariant statement is that you have to include both sectors. Just like for the closed strings, we included both boundary conditions, right? That we put both NS as well as R on each on the left as well as the right moving sector. Okay. So here, instead of having 4 sectors, there will be 2 sectors for any fixed boundary condition on the axis. Okay. Those 2 sectors are one where you use the same boundary condition at the 2 ends. Okay, if both ends are Neumann. Okay. The other one where you put opposite boundary conditions at the 2 ends. If both ends are Neumann or both ends are Dirichlet. If it's Was there a question?
Yeah, what did you say regarding the mixed thing? The Neumann one end Neumann one end
Yeah.
Dirichlet?
So if you have ND, right, then we will declare Ramon as psi mu equal to psi tilde mu at sigma equal to 0 and psi mu equal to minus psi tilde mu at sigma equal to pi, right? Because at the pi end, it has become Dirichlet. So this is the 0, 0 end, this is the pi end. And NS will be psi mu equal to, I have changed this one, psi tilde mu at sigma equal to 0 and psi mu equal to psi tilde mu at sigma equal to pi. So as far as the psi mu is concerned, we see that the NS with ND looks like the Ramon with NN. Right? NS with ND looks like Ramon with NN. Okay, and NS with and Ramon with ND looks like NS of NN. But on the X mu's, of course, the boundary condition is determined only by whether it's N or D. Right? There, you don't care about whether it's Ramon or the Neveu-Schwarz. Okay. So while in the psi sector, the spectrum will look the same, right? That if you change both, if you change N to D at one end and R to NS, right? It will look like you'll have the same kind of oscillators. Okay, we'll work out the oscillator algebra. And but in the X sector, it will be different. Is this clear? Because X sector, what is going to happen, right? At one end, you will impose del sigma x mu equal to minus equal to del. At one end, you will impose del sigma x mu equal to 0. At the other end, you will impose delta x mu equal to 0, right? For ND. So the x mu part of the spectrum will change if you change from NN to ND. Is this clear? No? Maybe when we work this out, it will become a little clearer. Yes?
If we put NN boundary condition on both sides,
Yes.
then the NS sector and R sector are same.
No. If you put, say, NN boundary condition, right? Then the NS sector in the NN boundary condition.
The same as the R sector in ND boundary.
Yes, indeed. That's right. Right? Okay, but this is only for psi mu, not for X.
For X, it would be different because.
Exactly. Because X only cares about whether it's D or N, right? Doesn't care about whether it's NS or R. Is it clear? Right? So right now, let's just proceed by saying that they have the same boundary condition. Later on, we will see what happens when they have opposite boundary condition, right? N and D. But this is relevant because sometimes you may have, say, two D strings, right? One goes in this direction, the other one goes in this direction. Okay? On that, there are open string excitations that go from one to the other, right? And there it's clear that for two of the coordinates, right, you have ND boundary condition, right? ND for one and DN for the other one, right? Because suppose this is the x1 direction, right? Then the x1 will have N boundary condition for this string, but D boundary condition for this string, right? And for x2 it will be the other way, right? So the ND boundary conditions do appear in various open string configurations, right? If you have complicated configuration of difference.
So when we write the spectrum,
Yes.
for this ND and NN boundary condition, so R sector states will be same or
R sector of NN will be the NS sector of ND, right? Because it will be the same twisting. X will change. Yeah, exactly. So when I say spectrum, that just means that the in the in the psi mu sector. Right? Ultimately, you have to put the physical state condition, etc. Then the spectrum will be defined. Okay, this is the spectrum in the full Hilbert space before imposing the BRST constants, etc. Okay? If you just focus on the psi mu sector, okay, then it is true that ND boundary condition in the Ramon sector will become NN boundary condition in the NS sector.
This mu has to, like here,
Hmm?
was it true, like for rotated branes, will it be true that I can set del x mu equal del bar x mu?
Yes, for rotated branes, for example, right, you can define x1 plus x2 and x1 minus x2 are the coordinates, right, if it's 45-degree rotation.
But I can do the same with fermions.
Fermions will follow automatically. See, the fermions, right, the boundary condition on the fermions will have to be correlated to the boundary condition on the x mus, right, except that fermion also has an opposite boundary condition because you have ns and r. Right? So the only freedom that you have in the fermionic sector by itself is to change ns to r and r to ns. Right? Otherwise, it will follow the same boundary condition as the bosons. Right? So it's best to start from the Ramon sector. Right? In the Ramon sector, the fermion will satisfy exactly the same boundary condition as the ns sector. Okay? Then, when you go to same meaning this, that there will be correlation between what boundary condition you put on the ns and what boundary condition you put in the on the sides.
Right. I mean, I was thinking like maybe if I don't rotate in boson, but I rotate in.
No, that you cannot do. Yeah, that's not allowed.
Once I choose the orientation for the train, then it follows.
Exactly. Yeah.
And the R sector will directly follow from X, then seeing this R sector will define.
Exactly. Okay. Seeing the R sector will define the NS sector simply by switching the sign at one end. Is this clear? So let's see how this affects the mode expansion. We have psi mu and expand modes. And I mean, we can also work out what the tau dependence should be, right? So I can also, we know that this R has been chosen in such a way that both B mu R tau, okay, and B tilde mu R tau evolves in tau as e to the minus I R tau. Right? So that this becomes a function of tau minus sigma, and this becomes a function of tau plus sigma. Okay, that's the way we had chosen to define our left and right moving modes. So with this, let's try to impose the boundary condition. At this stage, I have not said about what values are take. Okay, let's leave it as it is. The boundary condition at sigma equal to 0. Okay, tell us, so suppose we look at R sector. So this is psi mu at sigma equal to 0 is equal to psi tilde mu at sigma equal to 0. Okay. Let's say R sector, and now I'm on boundary condition so that everything is very explicit. So if you compare these, you will get that B mu R should be equal to B tilde mu R. Okay, I can put the tau dependence in any case. Let me write this so that Because if you want this boundary condition to be valid for all time, all tau, then these two can be equal only if these two are equal. The boundary condition at sigma equal to pi tells us that psi mu at sigma equal to pi is psi tilde mu at sigma equal to pi. Okay. So b mu r to the I r pi would be b tilde mu r to the minus I r pi. Okay. But b tilde mu r is already b mu r. Cycle, yeah, tau. I have chosen this in such that tau dependence is always e to the minus I r tau. Okay. The sigma, because otherwise the sum over R runs over all both positive and negative values, right? If the relative, if both are functions of tau minus sigma, then this will be the same. Right? But the difference is that one is left moving, one is right moving. So one is a function of tau plus sigma, the other one is a function of tau minus sigma. Right? And our convention is such that psi mu is a function of tau minus sigma, because that's moving to the right, right? As tau increases, sigma should increase. Oh, yeah, yeah. Thank you. Yeah, this is minus. This is clear? Okay. So this gives you, if you compare e to the 2I r pi equal to 1, and this means that r must be an integer. So for D, we have the same expansion. For D, same result. Okay. Except that because you will get a minus sign here, okay, in the first equation. So you'll get b mu r equal to minus b tilde mu r. You'll get another minus sign here, right? So you'll get b mu r equal to minus b tilde mu r. So that minus sign will cancel, but e to the 2 I r pi equal to 1, that will still be valid. Is this clear?
R has to be, but that is just true because it's Ramon.
Yeah, so that's why you call this sector Ramon. Because a priori, right, that Ramon and NS for closed string is different for compared to Ramon and NS for the open string, right? Either there are two sectors, right? And because this R is coming out to be integer, we call this Ramon. Okay. But as we said, if it was ND, okay, suppose it was ND, right? Then one of the signs will change here, right? Okay. Then it will become e to the 2 I r pi equal to minus 1. Then it will be R will be half integer, right? Okay. We'll still call it Ramon. Okay, so Ramon, so the general rule is that Ramon will have the same moding as the corresponding, that the psi mu will have the same moding as the corresponding x's. Right? You can check that in that case, if you have ND boundary condition, x will also have half integer moding. Right? We can try to work it out. Okay? Because it's the same argument, right? For x's, right? You write del x and del bar x. It will be similar alpha mu r, right? And this dependence. Right? And then we repeat exactly the same argument with psi mu replaced by alpha mu. Right? And for ND, there will be half integer moded. For NN and DD, it will be integer moded. Is this clear? R is C, exactly. So this is saying R is C in C. Okay? So that we call it Raman sector.
But and the boundary condition.
Yes.
Then for X also the modding will come out to be
Half integer.
for DD.
For DD and NN, right, the oscillators are the same. Psi mu oscillators are identical. For X's, right, there's only one difference, which is in the zero mode sector. Okay? Because for DD, there is no P mu. Okay, because you are forcing X mu to be constant, right? At the boundary, if you have a fixed constant, so that cannot evolve with time. So that's the only difference. That P mu, that component of P along the D direction is 0.
So the alpha mu 0
won't be there for the DD.
So the integer.
Exactly. Yeah. Is this clear? Okay, so for NS, let's just repeat this. That NS sector can still a normal boundary condition. Then at sigma equal to 0, we have psi mu equal to psi tilde mu. This implies B mu are equal to B tilde mu r. Sigma equal to pi, psi mu equal to minus psi tilde mu. So B mu r equal to minus, sorry, this is B mu r e to the power I r pi is minus B tilde mu r e to the minus I r pi. So this is minus B mu r from here e to the minus I r pi. So this gives you e to the 2 I r pi equal to minus 1. So r belongs to half integer, is c plus half. Is this clear? Okay, we'll come back to the spectrum in a little while. Just review the NS. NS for NN, not NS, sorry, X mu for NS, NN is del X mu. And del bar X mu. In the boundary condition, at sigma equal to 0 and pi, this tells us that alpha mu n equal to alpha tilde mu n. This is from sigma equal to 0. Okay. P mu and X mu have no condition, right? Because at sigma equal to 0, sorry, del X mu, I think I made a mistake here. If you take the already derivative, and just P mu. Okay, maybe there is some I or something times a constant. X mu has P mu tau, right? X mu has X mu plus P mu tau plus other things. Right? So from here you can work out a normalization for del X mu and del bar X mu.
The expansion for X had alpha mu n, right?
Yes, indeed.
So
Expansion
would
for
the-
X had both alpha and alpha tilde.
Yeah.
But when you calculate the holomorphic and anti-holomorphic derivative, or equivalently del plus and del minus, if you are using the Lorentzian coordinate, then one of them involves only alpha, the other one involves only alpha.
Yeah. Won't an iota n also come down?
Iota will come in, yeah, maybe there is some iota coming. Here you are saying, yeah.
Yeah, no, with alpha, iota n factor.
Alpha is defined so that in the expansion X mu, we have alpha mu n over n.
Okay.
So when you calculate the derivative, it's just alpha mu n, there may be some extra factors here, which I don't remember. There are some iota factors here, but no n, right? That's the way we have normalized alpha. So this gives to alpha mu n equal to alpha tilde mu n and alpha mu n e to the power I n pi is equal to alpha tilde mu n to the minus I n pi. So this gives to n belongs to C. For dt, we have delta of x mu equal to 0 at sigma equal to 0 and pi. This gives sets P mu equal to 0, otherwise same as Nn. This is basically saying that if you have a D-brane, right, then the open strings on the D-brane cannot carry momentum in the transverse direction. Right? Because on the transverse direction, you put Dirichlet boundary condition. And it is saying that along the Dirichlet direction, the momentum component should be 0, right? Which seems physical because once the D-brane is fixed at a given on a given surface, open strings can move along the D-brane, right? So it can carry momentum along the brane, but not transverse to the brane. Right? And that's what it is. This is saying. Is this clear? For Dn or Nd, at least one of the ends will have delta of x mu equal to 0. Right? That is enough to kill P mu. Right? So P mu will still be 0. So P mu will be 0. And the modes will be half integer. And alpha mu n will, with n belongs to plus half. Look at the argument is exactly the same as what we had earlier. Right? Basically, it will have, there will be extra minus sign. If at one end, if the 0 end is normal, you have this boundary condition. Right? And at the pi end is Dirichlet, right? So there will be an extra minus sign here. And that will make n to be half integer. Is this clear? Right? So this is basically saying that if you have a intersecting brane configuration like this, okay, then the open strings that are here cannot carry any momentum either in this direction or in this direction. Right? It's stuck. So it can only move along the common directions. Right? Common direction is normal. Imagine that you have two membranes, two-dimensional surfaces intersecting on a line, right, in 3 dimensions. Then along the line, the open strings can move, right, because there is a translation symmetry along the line, right? But it cannot move either away from the first brane or the second brane. Is this clear? Yes, that is a physical picture of how open strings behave on a system of D-planes. Okay, so mainly it can only move along the common Neumann directions. Neumann direction. Right? Because if both ends have n boundary condition, then P mu in those directions is not supposed to be 0, right? So that means the open string can move there. Right? And I am saying that this is also physical because imagine that you have a intersection like this, right? So this is one D-plane, this is another D-plane. Right? Open strings are going from here to here. Okay? They are still allowed to move along the line, right? Which is the common Neumann direction. Is this clear? So take NA not DD case. So if you have P branes, DP branes, this means that you have N along P plus 1 directions and D along 9 minus P direction. P mu in this case is along P plus 1 direction. Because along those we have N boundary condition. Okay. So the symmetric group let's look at Lorentz symmetric group. In 10-dimensional space-time, when you wrote down the formula, set up the problem, the Lorentz symmetric group was SO9, 1. Now we see that the mixing of the N and D directions is not a symmetry. Right? Suppose you may take part of the Lorentz group that rotates the N direction to D direction. Then the open string boundary conditions break it. Right? So now the symmetric group will be SO P, 1 times SO9. SO9 minus P. Because you can rotate among the Dirichlet directions, that's a symmetry. Okay. And you can rotate among the Neumann directions. Okay, that's also a symmetry. So Lorentz group then will break into this, right? Which again is physically clear what's happening, right? Imagine that you have in 3 dimensions, right? 3 plus 1 dimension. You have a D string, right? A line. Then what will be its symmetric group, right? One is that the open strings are moving along the line. So there is a 1 plus 1 dimensional Lorentz symmetry that it reflects the motion along this line, right? The symmetry, the Lorentz transform along the line. The other one will be the rotation in the transverse direction, right? That is SO2. Okay, this is just a generalization of that. But from the point of view of the physics on the D brane, on the DP brane, this one is like an internal symmetry. Yeah, I have chosen time to be Neumann. Okay? Because that's the case where you can physically interpret this as objects in the theory. Otherwise, you have to reinterpret them as instantons, right? Which we are not doing that now. Exactly, yeah. If you want them to have dynamics, time direction, you always choose to be Neumann. Right? So these are either particle-like objects or string-like objects or membrane-like objects. There's just objects in the theory.
Internal for this P+1 dimensional Wald volume theory.
Exactly. Right? Internal symmetry for this P+1 dimensional Wald volume theory. Once you have the big picture, right? Then this is part of the Lorentz group. Right? But from the point of view of the d-brane physics, right? If you just look at the open string on the dp brane, right? In essence, it doesn't even know about the existence of the extra dimension, right? Not directly. Okay? So, but there is nevertheless a symmetry along this direction. So you interpret this as an internal symmetry of the theory.
Formulation we studied. There it seemed like Lorentz invariance was related to central charge to the critical dimension.
Yes.
But here it seems like we are breaking Lorentz.
Yes, that is true.
So what happens to
central charge is still the same, right? Because the central charge, yeah, it's a local, yeah, exactly. Right?
Probably doesn't have anything to do.
Exactly, yeah. Right? So in this formulation, right, it's q square, which that you still have to ensure that q square is 0.
I still but how is the boundary condition going to affect that?
Because, for example, the q at least is not the old q anymore, right? Old q had both alpha and alpha tilde, psi and psi tilde, right? It had a both holomorphic and anti-holomorphic piece.
Right, like on worksheet it will be like I integrate JB on a line.
Exactly. You integrate JB on a line. Exactly.
And I have to not let the chart constructed that way. Should
Is nilpotent.
Square root 1.
Exactly. Right? And the point is, as long as you have chosen your boundary conditions correctly, right? So instead of exactly. So instead of, I mean, I formulated this by saying that the allowed boundary conditions would be when the T is preserved, or T and TF, right? You can also formulate it by simply saying that the BRST current should be preserved, right? That Q should exist, right? Even in the open string sector, right? And that Q has to square to 0. Right? So that itself, so that's the most general set of boundary conditions you can allow, right? Which preserves Q. Right? You have to make sure J sigma is 0 at the ends. JB, yeah. The sigma component of JB should vanish both at the both ends.
But you are saying in general, it's like both are equal. The energy momentum.
Yeah, yeah.
But they can be different.
No, energy momentum you cannot really, I mean, do very much because it's this. There is a C times energy momentum tensor, right? There is a term like that.
Like, maybe I can ask which one is like a bigger subset of boundary conditions.
I think as far as I know, that both are equivalent, right? That once you impose the energy momentum conservation on the TF conservation, right? That guarantees the BRST charge being conserved.
Now the spectrum should be representations of this group, not the full Lorentz.
Exactly, yeah. So open string spectrum, you should really classify according to representation of this group.
And the closed string spectrum will not.
Closed string spectrum will have the full Lorentz symmetry.
This boundary conditions.
Yeah, but at the level of the non-interacting theory, that presence of the d-brane doesn't affect the closed string.
And the reason is because closed string, the states we consider are like asymptotic in some sense.
Exactly, yeah. You can think of them as being far removed from the d-brane, That is true, but you can take the closed strings to be in the transverse direction separated. Exactly, right? Even if you have space filling brane, right, at the 0th order, right, the closed strings are not affected by d-branes. They'll start getting affected at higher order. Because otherwise, at strictly GS equal to 0, there's no interaction between closed strings and d-branes. Right? That's why exactly, we need at least one part of the string coupling to make that interaction.
But disk 1 point.
Yeah, exactly. Disk 1 point, for example.
Ashok, on that note, wouldn't
Yes.
the space filling brane change the cosmological constant and everything?
Yeah, it will do all that, but not at tree level.
I mean, but once the cosmological constant is, I mean, background is different, right? It's not.
But that's a loop effect. Right? Just like in a quantum field theory, right? It may happen that the tree level is perfectly well defined, but at one loop you find that there is a tadpole of a massless field, and you don't have a solution. Okay?
Oh.
Then the background will be destabilized. That can certainly happen.
I see. Okay.
Right? But if we're just doing naive perturbation theory, right? All I'm saying is that at tree level, the d-branes do not affect closed strings. Right? But that doesn't mean that the theory exists. Right? Once you go to one loop, if it generates a cosmological constant, then clearly, then you have to see if you can find a solution to the modified equations. Right? If you cannot, then you have to declare that the theory doesn't exist, that it's inconsistent.
But this
This
cosmological constant is at one loop, or is it at some non-perturbable?
At one loop.
Oh.
This system is what you told in, I think, type 1 within 32 space filling brane.
Exactly.
Cancel the technical.
Yeah. For type 1, right? In type 2b, okay, we'll discuss what kind of d-branes you have. But in type 1, you can have d9 branes, right? But if you just put d9 branes, then of course it generates cosmological constant. If you have a orientifold, right, that generates negative d9 brane charge, and then you have to put exactly the right number to cancel the charge. Okay, that cancels the charge as well as the cosmological constant, and then you have a supersymmetric solution. So the states will now have the form product over mu n alpha mu n. Times those states. Okay, this basically means that any state in the BC host system and any state in the beta gamma host system. Right? So this will be the general structure of the basis states. And K is P plus 1 dimension. Right? This is important. This is an NS sector. And in the NS sector, you build by state, we define K. As the SL2 infinite vacuum. Okay, which basically means that Lm 0 and Lm plus minus 1 on the vacuum is 0. And then K we defined as e to the I k dot x on 0 action on the vacuum. Okay. And in particular, it is important that the vacuum is unique because these modes are half integer. In the NS sector, R is half integer moded. So there are no zero modes in the fermionic sector. Okay? No fermion zero modes.
This is NS sector with DD boundary conditions or NN boundary conditions?
Yes, NS sector with DD or NN. Yeah, so right now I'm only considering DD and NN. This means vacuum is unique. The vacuum was fourfold degenerate. Oh, that's from after you include the ghost sector. That's what you meant? Yeah. So this I'm only talking about matter sector. Right? Ghost sector will be twofold degenerate, just like before, right? This just like bosonic string theory, we have twofold degenerate states. That will also happen here. So in the Raman sector, with NN and DD, the R is integer, which means that there are B mu zeros, and they have the standard anti-commutation relation. And this basically means that the ground state is a spinor. The spinor representation of 9 plus 1 dimensional 3-fold algebra.
Have we forgotten about GSO projection or has it already been accounted for?
No, they are there. Ultimately, I mean, after you construct this, you have to put the GSO projection.
Okay.
Right? This part is exactly as in the case of closed string theory, right? Except that in this case, you don't have separate left and right. So there's only one GSO projection that you make. See, because B tilde mu oscillators are set equal to B mu, right? So only one GSO projection you can make, right? And that will be similar to what what we had for closed strings.
Think about boundary condition in BC and beta.
Yeah, we didn't. BC will be identical to what we had for the bosonic string theory, right? So which basically means B is equal to B tilde and C equal to C tilde at both ends.
And this follows from some fact, right?
Basically Q, again, if you try to twist B at C, right, then Q will have trouble. Yeah, you don't have much options here. Exactly.
For beta gamma?
For beta gamma, the boundary condition is correlated to whether its Ramon's or NS. Right? Because see, TF we saw can have half integer mode, right? Because X can have integer mode, psi can have half integer mode. So TF in the NS sector, TF has half integer mode, right? So to compensate for that, it better be that beta gamma has half integer mode. Okay? So you choose the beta gamma boundary condition so that in the NS sector, they have it's beta equal to beta tilde at one end and beta equal to minus beta tilde at the other end, and similarly in the R sector. Okay, it's opposite. So there you have the same boundary condition of beta and beta tilde. The beta equal to beta tilde if you choose on one end, then beta equal to beta tilde also at the other end.
For the BC if I remember correctly, in the bosonic case, there also this T beta, T BC was there. There
Yeah.
also T sigma tau component.
Exactly. Right? But on top of that, you also have to have the the Q being preserved, right? So that's also important.
This both will not be equivalent. Like if we
Yeah,
have this
eventually this will be equivalent, but you have to check that this is true. Okay. For example, the beta gamma, right? Why is it correlated with psi? Right? If you choose the Ramon sector of psi, you have to also choose Ramon sector of beta gamma, and vice versa. Right? That one way to see this is that the Q has to be constant. Right? If you had Ramon sector for the psi and the NS sector for beta gamma, right? Then beta gamma will be half integer moded, psi will be integer moded, right? Then Q will be ill-defined, right? You will not have the zero mode of the BRST current. Exactly. So that correlation also has to be there.
Ashok,
Yes.
uh, the spinners are 9 plus 1 dimensional, you're saying?
Yeah.
Not P
So
plus
at
1.
this stage, they are 9 plus 1 dimensional, right? Because there are all the 9 plus 1 B0 are there, right?
Yeah.
But to get some physical information out of it, we have to decompose the 9 plus 1 dimensional spinner into this subgroup. SOP comma 1 times SO9 minus P. Okay, so these will basically become spinors and SO9 minus P. Okay, this is just by decomposing the original 9 plus 1 dimensional spinner into representations of the subgroups. Is this clear? Okay. In particular, the fact that these are spinor of SOP comma 1 means that these are fermions. Which decomposition? Yeah, because any representation, right, can be decomposed into the subgroup, right?
spinner.
Yeah, and the spinor always goes into the spinors of both. Right? For SO groups, the spinors of SO, bigger SO group goes into the spinor, the product of the spinors of the subgroups. Because you can see that you could have done this analysis separately in the SO9 comma 1 and SO 9, sorry, SO P comma 1 and SO9 minus P, right? Yeah, it's visible from there. So it has to be spinors of both. So the R sector states will be given by the same kind of product. Zero, R greater than 0. Sorry, if you to put in minus, so I should put minus there. If you SQ can only be 0 or 1, right? Times A, which is the spinor index, and then times the host states. Then you have to impose
There's
guess.
a K also, right? A comma K.
Yes, thank you. K comma A. Yeah. We put GSO projection plus Q cohomology condition. And then you have the usual relation that if you have a generic K, so I should also say that you put Gauss number equal to 1. Okay, just like for the closed strings, you impose a Gauss number equal to 2 condition. Okay, in the cohomology, you put a Gauss number equal to 1 condition, and then the for generic K, we can choose representatives. So NS sector, we can choose VM times C1 on 0 ghost, 0 is of the BC times e to the minus phi 0 on beta gamma. So this is a -1 picture vacuum. And now you don't have separate left and right sector picture numbers because the boundary condition relates them. Right? The boundary condition relates the expansion modes of beta with expansion modes of beta tilde and of gamma with gamma tilde. So you really have only one sector. Don't have separate left and right sector.
This Gauss number equal to 1 condition came from this only, no? That we can choose representative of this.
Yeah, but the point is that you can have also C0, C1. Just like in the for closed string, if you remember, right, that we had said that you can choose representatives in the Gauss number 2 and Gauss number 3 sectors, right? So Gauss number 3, we said that okay, we have to choose make one choice, and we make Gauss number 2 as a choice. Similarly, the natural choice here is the Gauss number 1 sector. So the VM here is a dimension half superconformal primary.
Sorry, this choice was there even in the free particle case.
Yeah, exactly. It was there even in the free particle case.
Sectors and clause.
Exactly. Yeah. Right? When we studied the non-relativistic particle, this choice was there. Because you have to declare which host number you consider as physical. Okay, so superconformal primary basically means that LM acting on VM equal to 0 and GR acting on VM equal to 0 for M greater than 0, R greater than 0. And L0 on VM is half VM. Right? That's the statement that it's a dimension half superconformal primary. Total dimension adds up to 0 because this also has dimension half e to the minus phi of 0. Okay. And this has dimension -1, right? Because it is C1, which gives the L0 eigenvalue -1. So this is -1 plus half. That gives you dimension 0. Is it clear? And similarly in the R sector, we choose this to be Vm times C1 on 0 times e to the minus 5 by 2, 0, 1, 0, right? This is in the picture, you can choose in picture number minus half or minus 3 half, those are the canonical ones, just like in the case of closed strings. So this should have dimension T8, sorry, dimension 5, 8, because this has dimension 3, 8. Okay, these calculations are the same as the ones that we had done for the closed strings, right? Except that you have only half of the sector. And these are minus 1. Okay, let me just say something about the massless NS sector states. Just a few minutes and then I'll stop.
One point we discussed that at zero momentum,
Yes,
the electron was something different.
Exactly.
It doesn't take-
yeah,
That also had ghost number 2 condition.
yeah, yeah. Because that was C1, C minus 1 minus C bar 1, C bar minus 1 on the vacuum. So total ghost number was still 2. Right? Yeah, so we don't want to go outside the ghost number condition. Okay? But you don't have separate ghost number, you don't specify ghost number in the left and right sector separately. Right? Because it's a total ghost number which is important.
At generic momentum, we can always write the states in that form, C tilde. And here it's C on vector.
Here it's only C, yeah. So generic momentum, you can always choose the representative of the BRST homology to be of this form. Okay, maybe I'll do this next time. Right? So basically, next thing we'll study are the massless sectors, right? The open string massless sectors, and I mean, again, as in the case of bosonic string theory, the massless sectors, there will be two important class of massless sectors that come from open strings. Right? One is which gives the transverse motion, okay? Because given a D brane, you should be able to move it, right? That's
The D brane itself.
D brane itself moves it. So that's the expectation from scalar field, massless scalar field. Okay? There has to be one set of modes, and then other one is a gauge field that lives on the D brane, right? So there'll be two kinds of massless modes, and then we'll also get massless states from the Raman sector, okay, because of the supersymmetry, right? The supersymmetry will require that there are some massless sectors in the Raman sector. And we'll also study the supersymmetry of D branes. Okay, what kind of supersymmetry it preserves. Okay, so I think I'll stop here.
So we can choose the D brane configuration to break all of this.
Yeah, we can. Yeah, you can certainly choose the D brane configuration to break all the supersymmetries. Right, and we'll see that when you cannot preserve more than half. Basically, because what will happen is in the closed string sector, if you recall, we introduced the supersymmetry generators. There is a set of holomorphic generators and anti-holomorphic generators. Right? Once you have a D brane, right, you have to put boundary condition on those, and it will automatically relate the holomorphic and anti-holomorphic parts. Just like it is doing for the size. Right? So once you have fixed the holomorphic part, anti-holomorphic part gets fixed. Okay, that's why you cannot have more than half the supersymmetries. So each D brane will break half the supersymmetries, right? It will break at least half the supersymmetries. No, space-time. Yeah, space-time, you remember you introduce sigma is, right? And sigma tilde is this e to the minus 5 by 2s.
Oh, right.
Right? Yeah, so these ones.
Are the space-time supersymmetric.
Exactly. Right?
And since now you have to.
Yeah, so now there will be a boundary condition that will relate this A or A dot. Right? The A or A dot depends on whether it's type 2A or type 2B. Okay. But now what's going to happen is the supersymmetric the boundary condition will relate these. Okay, so you don't have two independent generators. Okay, you have at most one. Or at most one set of independent generators. Okay, so we'll continue next time. Okay.
Yeah, like where does the overall topology of target space come into play? in this
Overall
construction?
topology means, of course,
Like,
you have
like if I just consider say boson,
Hmm.
one boson compactified.
Okay.
Yeah, there also I have Dirichlet and Neumann
Exactly.
choices.
Yeah, yeah.
But like this choice of boundary condition, is it affected by the overall topology of the target?
No, you can have both conditions. Right?
Like, yeah, it seems like
Yeah.
whether it's X is compactified or uncompactified, it's the same choices.
So yeah, it's the same choices, right? But the spectrum will be different. So you can
Yeah.
think of it the other way. Suppose you have a D plane, right? And now you have a possibility that either the tangential direction is compactified or the transverse direction is compactified.
Okay.
Right? If the tangential direction is compactified, then the momentum gets quantized.
Okay.
Right?
And transverse, then it will.
If the transverse direction is compactified, then the momentum nothing happens because momentum is along the non-compact direction.
It will be continuous.
It will be continuous.
But winding.
Yeah, now you have a winding mode, right? Where you start from earlier the DD boundary condition, right? Both ends, you start from one end and then end there, right? Now you can go by 2 pi r. Right? That one end may be at x equal to 0, the other end may be at x equal to 2 pi r. Right? That's still a periodic. That's still, it's what should call it periodic. You are basically coming back to the same way.
Like open string can originate from D plane and wind around the direction and then
End of
come
it.
back.
Exactly. Right? But you should distinguish this from closed string winding, right? That if the D plane is this way, right? And suppose the transverse direction is periodic, right? Open string can come go like this, wind around, and come here. Different point. Right? Because open string are not demanding that it's periodic. Right? It can end on D plane. That's all we have.
Yeah.
Right? So this end can be here, that end can be somewhere else. That's like you are allowed this kind of open string, right? The D plane, they have both ends at different points. See here all the differences are these are still a different point, but they're going all around the others. So these are loose ends.
Correct. But that will appear in spectrum.
Just appear in this one. Yeah. Both tangential direction also appear, right? So the T will be quantized.
Yeah, yeah, my states will change.
The states will change. Yeah.
Will that carry extra label?
Exactly. Yeah.
But it seems like, I mean, still, I mean, if the starting point is just that T bar condition, the T equal T bar at the boundary, something like that is my starting point. It seems like very ignorant to the fact that how is my target?
Yeah, because it's local, right?
Yeah.
You're just putting the boundary condition locally at the two ends. Right? The boundary condition, this target topology of target space, basically tells you what's happening in between.
Yeah.
Right? Because if you just look at these two ends, right? These two ends are the same as this, right? So the topology of target space is in the line, right? Away from home.
Yeah, yeah. I guess, yeah, maybe it's, I don't know if it is a general fact that the kind of boundary options I have for boundary conditions are not affected by the target space, rather the spectrum is affected by the target space topology.
You can think of it that way. On the other hand, you can also say that on one end you have x equal to 0, the other end you have x equal to 2 pi. Right? So in that sense, the boundary condition is affected.
Okay.
Right? If you just open this up, go to the covered space, right? Then it becomes x equal to 0 at one end and x equal to 2 pi at